All right, here we go again. Pulsars and stars. First off today is June 28th, 2015. Pulsars versus stars. Now, establishment science has a pulsar forming from a collapsing supernova and then doing all this weird crap, and becoming neutrons and all this other stuff. I would ignore their interpretations because, number one, they try to fit these objects with stars. But as you'll see, they are not stars. They are something else altogether. In the theory I'm drawing up, a pulsar is an embryonic galaxy. It emits beams of electromagnetic radiation. There are only a few thousand of them in our galaxy. They're very rare. The magnetic field strength is 10 to the 15 Gauss for the strongest ones, and 10 to the 11 Tesla, that's the same number, which is its magnetic flux intensity, how strong the magnetic field is. It's very, 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 very strong. They're only a couple kilometers in diameter, meaning they're very small. Their formation requires runaway magnetic flux compression, meaning you have to figure out a way to compress the magnetic field really, 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 really strongly. They store incredible amounts of magnetic energy as a result of the runaway magnetic flux compression. I think they're superconducting. As well, their shape is probably a torus. It's not a spherical object. It behaves very strangely, which means it probably has a different structure altogether than a star. On the other hand, we have stars. A star, according to stellar Metamorphosis, is a young planet. It's a very hot young planet. They shine in all directions evenly. The old stars don't shine, obviously, because they're not undergoing plasma recombination, which is an exothermic phase transition. There are hundreds of billions of them in our galaxy, meaning they're very common. All you have to do is look up in the night sky and chances are you'll see one. You're probably even standing on one, a black dwarf. The magnetic flux intensity is only 1 to 2 Gauss, which is probably the global magnetic field. Now that's incredibly weak compared to a pulsar. A pulsar will eat this one for lunch compared to its magnetic flux intensity. Stars are thousands of kilometers in diameter. They're very massive. They're much, much larger than a small pulsar. Their formation requires coherent, stable ionization, meaning you have to ionize the cloud. Gravitation doesn't ionize. You have to have large electrical currents flowing through a cloud to make that material ionize, and then you also have to magnetically compress it. So that would have runaway magnetic flux compression. This would have temporary magnetic flux compression, which means the evolution of the star probably branches off. So say you have a cloud up here, given the material, will determine what the thing becomes. So if it becomes a pulsar, it branches off over here from having too much hydrogen and helium being superconducting. If it has too much iron, nickel, silicon, and various other components, the gas cloud will become a star, given both have the same amount of current flowing through them. But that's theoretical. I'm not going to work on that right now. 7. A star stores energy in gravitational field, and it releases this energy as chemical reactions, and the heated matter cools down. It's basically thermodynamics. If you have a plasma, it's going to recombine into a gas. That gas is going to that gas is going to condense and deposit a solid and liquid structure. That's what stellar evolution is. It's planet formation, in case you didn't know. Number 8, a star is electrically conducting, but it gains resistance as it evolves. The star's plasma becomes gas, and it starts resisting electrical current flow, which means it'll start dimming considerably as the material starts differentiating in its interior via Markman convection. I went over an earlier video overviewing that. And 9, last but not least, a star is spherical throughout its evolution, meaning after the star is born, it's hot, and it cools, and it shrinks, and it keeps its round ball shape, which means it's probably much different than the torus of a pulsar. So as we can see, stars are not pulsars, regardless if the very definition of pulsar means pulsing star. It's a shorter version of pulsing star, but as you can see, those things that pulse are not stars at all. They're something else entirely. As well, I wanted to overview, because you're going to see this in a lot of literature, you're going to see how pulsar is somehow a neutron star, or it's a rotating neutron star, what they want to tell you, that forms from the core of a star collapsing and exploding, or whatever kind of nonsense they think up. But instead of metamorphosis, the star is a very coherent, stable structure. If it collapses, as it collapses, it radiates the heat away, and it combines the elements into molecules, forming things like land and water and an iron core, and it doesn't collapse and explode into some grand supernova event. If the supernova event is real, it probably has something to do with a pulsar, not a star, and that's what I want to get across to my viewers. Today, as you can see, was June 28th, 2015. If anybody has any questions or comments, please leave them below.